Now, ladies and gentlemen, we start direct current machines. In this introduction, I will use that file and I have downloaded. Here it is. Let's start DC machines. First, make an introduction and then talk about construction and armature windings. Let me introduce the machine first. Most of the electrical machines in service today are AC type. DC machines are of considerable industrial importance. Since our today's network is AC, we generally prefer AC machines. The machines can be operated under alternating current conditions. But there is another machine. It is getting rare today, but it has a considerable industrial importance because their characteristics are very unique. We will talk later. DC machine mainly used as DC motors and DC generators. I mean, DC machine is mainly used as DC motors. And the DC generators are not very common today. They are rarely used because today there is no difficulty in producing DC today. Generating DC is easy today. For example, you can generate AC by using synchronous generators, let's say 3-phase. You apply some mechanical input power to synchronous machine. Let's say here's the excitation circuit, apply some field current. And then you will induce or generate some AC here on armature terminals. For example, by using 3-phase rectifier, doğrultucu, you can convert that 3-phase AC into DC. And it will be easier after such an enhancement in power electronics. After the 70s, power electronics gets cheaper and cheaper. So we prefer an alternator, I mean synchronous generator, together with rectifier. That was the general case. For example, in automotive industry, till 70s or 80s, generally there were DC dynamos in automobiles because electronics was expensive till 70s. But after 70s, power electronics diodes gets cheaper and cheaper. So instead of using DC dynamo, we have changed topology into alternator rectifier combination. Let's say car alternator. Here you see a device, alternator. In fact, it produces AC inside, but there is a rectifier block. Here is the rectifier block or module installed in synchronous alternator. It is somewhere here. It is in the body. It is incorporated. It is inside the system. Here you see diodes. 1, 2. Here are some diode bridges. 3-phase rectifier. And here you see 1, 2, 3 diodes, disc diodes, rectifier diodes. 1, 2, 3, 4, 5, 6. 6 diodes for three-phase rectification, you see, three-phase rectification. Okay, today we prefer those machines as motor because the DC generators are not common today. Especially we see DC generators in old ships manufactured in 1920s, 30s, Second World War. During that period, the system contained DC dynamo. The competition between this system, I mean alternator plus rectifier system, and competitor is DC dynamo. It requires much more maintenance, So it costs expensive. Reliability is poor a bit. Not dramatic, but a bit poor reliability. I mean, you will send these machines into space, for example. There are some frictional parts. And there will be some changes under changing temperatures, for example. So there will be some failure. Reliability is a little bit poor. But the competitor alternator and rectifier system is cheaper than DC dynamo, requires less maintenance, and much more reliable. So today we prefer this guy. Alternator and rectifier. So dynamo usage is very rare today. As a motor, yes, there are some usages because they have very distinctive, very unique characteristics. For example, in a startup process of inner combustion engines, I mean, we use starter motor as a starter motor in automobile sector. Marş motor diyoruz, starter motor. Starter motor used for inner combustion engines are always DC serial motors. We will talk later. Because it is very tough or difficult job, starting process of a car is very difficult job, but there is a motor can handle this. It is DC serial motor. We will talk. Very unique characteristics. Supplies much more torque than other competitor motors. So we prefer DC motors. Even if it requires some maintenance, there is no other good solution. We prefer DC motors in automobiles and trains, for example. DC motors provides a fine control of the speed, which cannot be attained by AC motors. Speed control is very easy in DC motors, and you can manage very precisely, very fine control by using very cheap methods. Easy methods can be done by DC motors, but in AC motors it cannot be attained. It is difficult to manage speed control so easy, so cheaper. That is much more advantages in speed control. DC motors provide very fine properties. It is easy to manage speed control, and the speed control method implementation is easier. For example, by using only a single rheostat, you can manage speed control precisely, but you cannot manage in AC motors. DC motors can develop rated torque almost at all speeds, from standstill to the rated speed. You can develop or produce rated torque. I mean nominal torque. You can easily adjust torque. You can maintain it in a large speed region. Let's say here is the speed. Let's say that is the rated speed. And then till rated speed, mechanical torque will be kept constant. That region is constant torque region. After that point, from 0 to rated standstill to rated speed, you operate machine in constant torque region. After that region, you operate machine in constant power region. That is constant output power or power region. Torque power. Okay. Those are the operating modes of the motor, DC motor. In fact, I talk about those regions in induction motor and synchronous motor. In all motors, we want to operate system in constant torque region in such a speed range, but over rated speed, we operate systems in constant power region. Developed torque at standstill is many times greater than the torque developed by an AC motor of equal power and speed rating. Okay, it means here we have a DC motor, let's say. Here we have AC motor. Both have the same power, output power, but the torque attained at standstill position when the speed is 0 is much more larger than the torque generated at standstill in AC motors. Torque standstill DC will be much more larger than torque standstill in AC motors. So that is very attractive property, very attractive. For example, you are doing very tough job or difficult job. For example, you are drilling in a mining industry. You need much more torque. For example, in trains, here's a diesel electrogen. Everybody remembers such devices. Here are some locomotive types. To start up such a large diesel engine, you need an electric motor. You need battery system. We use DC series motor to start up such a large locomotive because such systems under standstill conditions require much more startup torque. Only DC motors can give such high torques. So we prefer DC motors for startup purposes in locomotives. We also use DC motors in traction. Let me show you traction motor in locomotives. Locomotive DC traction. Okay, DC traction motor. Houston. DC traction motor. In fact, here are, that is the DC traction motor. One for rotor. This is the, let's say, rotor port. That is the stator port. There are at least 2 ports, electrical. Another DC traction motor. That is a bougie, a special truck, car element. Bougie motor somewhere here. For example, for traction in locomotives, it has been used over 100 years. DC motors are still in use, in fact, over 100 years. That is traction. There's another type of DC motor. DC serial motor. And one of his sister or brother is AC commutator motor, or generally it is called as universal motor. Especially after the Second World War, universal motors are applied in traction sector. This guy, it looks similar. The similar machine made a proper design to operate under alternating current. In fact, there is not much difference. It looks the same. For example, let me show you. Universal motor in images. Here you see an universal motor. And let's say DC motor. Images. Here are lots of products, but cutaway section, I mean, cutaway. Okay, here, okay. Here it looks like the previous one. This guy. Let me find. This guy. That is a DC motor. That is the universal motor. Let's take care on rotor. Rotor has some slotted construction. There are some coils. There is a commutator system that is the device called commutator. And here you see commutator. Here are brushes, slotted rotor construction. There are some coils. Almost identical. Only the material used in stator is a bit different. For example, here in stator, we use permanent magnet in small powers, and then we use some cast iron systems. It is this sort of cutaway poles. Here you see poles, DC poles, and yoke mechanism or frame. In fact, frame is cast iron here. We will talk later in detail. Frame looks like silicone steel sheets. This version belongs to universal machine, and the machine having cast iron or soft iron yoke or frame is a DC machine. The only material will change in stator, because in AC there is iron losses, core losses, because there is an alternating current inducing Foucault or eddy currents. They cause some eddy current losses and hysteresis losses. So to keep those kind of losses, we generally use silicon steel sheet material in AC machines. Tata, the AC brother is universal machine, so only stator material, let's say use cast iron, dökme demir, cast iron in stator. But here, stator and yoke or frame, I will introduce you later, yoke or frame. But here, the same parts manufactured by using silicon steel sheet material, just like in transformers. The material is changed. And all those machines are serial type. We will talk later, understand later. That was the introduction. Let me show some pictures. Here you see rotor. Here are some conductors you see, conductors. Let's say armature conductors. Here's a special device we learn that it is commutator. And here are brushes. One brush, another brush. Brushes. That is brush holder. Here are two poles. Let me show you. That is the pole coil, field coil, pole or field coil. Here's the pole core. Here's another part, but it is not very clear. But you see pole coils or conductors, pole or field. As you see, magnetic field, main magnetic field is produced in stator. It is just opposite of synchronous machine. Mohammed asks whether DC motor should have a magnet. Yes, there, to make energy conversion, we need electromagnetic field. But that electromagnetic field, as you say, can be generated by using DC field current or by using permanent magnets. Both are okay, but especially in small power machines, we use permanent magnets. In toys machine, for example, let's say DC motor. If you say DC motor, you see lots of toys motor. Those are for toys. You know, in every day. Here are some propellers for drones. Here are some high torque motors. This part belongs to gearbox. That is a motor for screwdriver, electric screwdriver. And those type of small power motors are generally made of permanent magnets. Magnetic field is generated by permanent magnet. In fact, permanent magnet, okay. Here you see, let me find permanent magnets, okay. Here it is. Permanent magnets on the stator, you see. That is the armature or rotor. You know, armature is the place where energy conversion occurs or where the electromotive force is induced. Here are the brushes. There must be some commutator here. We will talk later. You see permanent magnets. Again, the figure or form is a little bit different. It looks like square and round. It is round here. It is flat here. So inside you see here are two poles having permanent magnets in stator. The part connecting those two permanent magnets is called as frame or yoke. Yoke or frame. Yoke Türkçesi boyunduruk diye geçiyor. Boyunduruk. Let me draw it here. Here's, let's say, here's a permanent magnet. Let's say N pole. Here's S pole. Let's say permanent magnet again. And inside the poles, there is a rotor having armature coils. And here is commutator. And here are brushes. And then, ladies and gentlemen, take care. Something is missed here. Magnetic field coming from N pole passes through air gap, cuts rotor, passes through air gap, reaches S pole. But that is not it. Magnetic field lines must complete its path. So we need yoke. Here is frame or yoke. Another part made cast iron or soft iron material, ferromagnetic material. It is cheaper, so we use them. That magnetic field lines will complete their contour, their orbit. Okay, that's it. You see, this part is called as yoke or frame. Those are permanent magnet blocks in green, made of neodymium, for example, neodymium iron ore. Those are different materials constructed by different elements, and then those parts will be mounted together with the yoke to construct stator. Okay, let's find it again. Here it was. You see, here are permanent magnets. Those permanent magnets inside the frame construct stator. That is the main magnetic field. Inside the stator, there is a rotor having armature coils. That armature coils will induce electromotive force. You see the form factor, and it is due to the design. And here was another design, round design. It was somewhere there, but I couldn't find it right now. Here you see permanent magnets in blue and pink in stator, but as you see, yoke is not there, cannot be seen there. So that is not a real machine. That is the machine for only introduction. To have an efficient machine, you need full magnetic circuit like this. Magnetic field, let's say, coming from N pole, passes through air gap, cuts armature conductors in the rotor, and then passes air gap, reaches the opposite pole, and then completes its circuit. Magnetic field lines must complete its circuit. We were talking about the design. You see yoke. Let me write it down here. This is frame or yoke. Let's say Turkish boyunduruk. The piece connecting the poles. And it must be ferromagnetic. It must be as cheap as possible. Here are bearings, ball bearings. And here you see shaft. Here's the fan for cooling purposes. It is not clear, but here is terminal box, terminal or connection box, and then it looks cast iron, not aluminum. For example, in synchronous machine or induction machine, frame can be made of cast aluminum. There is no need to use ferromagnetic material in frame or yoke. In fact, not yoke. There is no need to use ferromagnetic material in frame. But in DC machine, frame is the essential part of magnetic circuit. Essential part. Okay. Here you see. Frame is the essential part. Magnetic field passes through frame, completes its circuit over frame. But in induction machine, let me call it back. Induction motor sheets. Okay, let's say sheets first. It's somewhere here. Okay, here you see. Here is the sheet material, the previous. You see the stator. Stator coils are located in those slots. Yoke is here, and all those made of silicon steel sheet material. So that is the stator made of silicon steel sheets. Yoke is the part of stator. This part can be installed in stator, in a frame. Let me show you. Here's the frame, for example. That is the frame for cooling, carrying, connecting purposes. Frame will be made of aluminum, will be made of cast iron, but I mean it is not required to have ferromagnetic material, because magnetic field lines complete its circuit in stator sheets. Let's say magnetic field passes through here in rotor and completes its circuit like this or like this. Again, that is the stator of induction motor or synchronous machine. All those similar. All those parts are made of silicon steel sheet material. But in DC motor it is a bit different. We can make it cheaper. by using cast iron, ordinary cast iron, because there is no alternating current. There is no eddy current and Foucault or hysteresis losses in the yoke part. So there is no need to use expensive ferromagnetic materials. We can use simple cast iron materials and it will be cheaper. Again, yoke or frame conduct magnetic flux and it also be used for cooling purposes, some mounting purposes. Here are feet for the mounting. Here is terminal box. Here are the fan guard, front guard, kapak. Another cross section. You see brushes. Here are a group of brushes touching to the commutator. That is commutator. Commutator. We will talk later. And here are brushes touching. That is rotor. On rotor part, you see armature coils, armature windings. That is shaft or output shaft or driving end. Driving, sometimes we say driving end. This side is non-driving end. Sürücü olmayan uç. Genellikle burada fan bağlı oluyor. This is driving end. The opposite of the driving end is non-driving end, or fan will be connected here. And then here is the seal. Sometimes it is sealed, not necessary. Here are bearings, ball bearings. Seal burada mühür, sızdırmazlık contası anlamına geliyor. Her zaman gerekli değil. Bazı proseslerde gerekir. Here are ventilation ducts. Kanallar, açıklık anlamına geliyor. Slot deyince biz daha ziyade şunu anlıyoruz. Şuradaki şeyleri, slotlar. Oluk. Ama orada da slot, sen yanlış anlamayız. O da slot aslında ama soğutma lafı geçtiği zaman duct daha çok kullanılıyor. Here's the wiring box or terminal box. And then you see the poles. Let me change color. Here are field coils. There is another field coil. For example, it looks like 2 or 4 pole machine, but it is not clear because it is a cutaway. Bu bir kesit olduğu için şurada bir tane kutup gitmiş mi gitmemiş mi göremiyorum açıkçası. Şekilden okuyabildiklerimiz bunlar. Şekil okumak bizim için çok önemli. Here are mounting feet. One foot is here, another foot is here. The construction. Okay. It is just opposite of what it was in synchronous machine. For example, in synchronous machine, in a practical synchronous machine, we install armature coils in stator part. But here in DC machine, we install armature coils in rotor part. In synchronous machine, the main magnetic field is generated in rotor part, but here it is just opposite. Main magnetic field is produced in stator part. Again, synchronous machine magnetic field will be designed by permanent magnets or electromagnets. Here it is either the magnetic field can be generated by permanent magnets or electromagnets. Here is the pole. Sometimes we say pole core. Pole core. Pole core. Demir, kutbun demir kısmı. Şimdi değerli arkadaşlar, burada pole core'da bir miktar demir kaybı oluşuyor. O yüzden pole core malzemesi silikon steel'den yapılıyor. Silicon steel sheets are used in pole faces. Şu yüz kısmına pole face deniyor. Kutup yüzü, kutup ayağı. Türkçe'ye ayak diye de girmiş, yüz diye de girmiş. Pole face. Pole face. This part we know yoke or frame. Generally made of cast iron. Cast iron. On the pole core, you see field coil. Field coil or field winding. That is the pole axis. Sometimes we say D-axis. Here you see pole core. I have already written here. I have said Yoke frame. It is written here. Here are feet mounting feet. Okay, that is the stator. Stator is the part where we produce magnetic field in DC machines. Stator is the part where main magnetic field is produced. That magnetic field will be generated by permanent magnets or will be generated by using electromagnets, just like here in this page. Again, inside the stator you see a rotor, and then here's the shaft, you see. Here are some slotted construction. Slots carrying armature winding. There are some windings we have already seen here. Here you see armature windings. Here are slots. Rotor again made of silicon steel sheet material. Made of silicon steel sheet pack. Yes, here would be some rotation. You can let me show you why we need to use silicon steel sheet material in rotor portion. Take care. Let's say here's N, here's S pole. When you rotate rotor, this point, for example, it is just under the N pole right now. And then when it moves down to here, the red dot given here will be here because of rotation. So this point will be under changing magnetic field. So you know it is a reason to induce electromotive force in the armature core. These iron parts will induce some electromotive force and cause some eddy currents or Foucault currents, and then some iron losses. Iron losses will be occur in rotor iron parts. So to keep iron losses as low as possible in rotor, we use silicon steel sheet material, isolated sheet pack. Let me show you DC armature. Here you see some silicon steel sheet pack. You see sheet pack. It is very clear. You see some sheets packed together. You see slotted construction. Here are wooden wedges. Wedge. Let me write it here. Wooden wedges. Wedge kama demek. Merkez kaç kuvvetle şu bobinlerin dönerken oluktan dışarı fırlamasını engelliyor. To keep coils into the slot, we use fiber wedges, sometimes wooden wedges. Here you see some wooden wedges. Here are copper coils. End of the copper coils will be connected to commutator. You see commutator. That is rotor. Rotor carry armature winding. Armature winding is installed in the slots of rotor. Rotor made of silicon steel sheet material to keep iron losses as low as possible. Here you see some, here you see shaft. That is the armature. Sometimes we say armature, sometimes we say rotor. In DC machines, generally both words are used for this figure. If you say DC rotor, it's okay. If you say DC armature, it's okay. Armature. That is the place where energy conversion occurs or where electromotive force is induced. On the right-hand side, right-hand side, you see a four-pole machine. Here are electromagnets. You see N, S. All electromagnets are connected series from here to here and here to here. All those coils are connected series, constructing field winding. You supply always DC to these field coils. DC field current is applied to construct stationary DC field NS and S. If you not change the polarity applied here on field terminals, the magnetic poles will be constant here, N and S. Here you see a four-pole machine. Inside the four-pole stator, you see an armature or rotor carrying armature windings. Here you see commutator. Here are some brushes. Here are two brushes, you see. Brushes, carbon brushes. Here you see a slotted construction. Slot teeth. Those are called as teeth. Here are slots, and the armature conductors are located in the slots of rotor. And rotor magnetic circuit is made of silicon steel sheet material. Here are feet for mounting purposes. Here would be a hook sometime to carry on, to move. Here you see yoke, steel yoke or iron yoke, or cast iron would be cast steel and cast iron. It doesn't matter. Iron and steel is similar. Steel has much more carbon. Base is main material is iron or ferro iron. Okay. Field windings, pole faces. Here you see all those called as pole core. Sometimes we say pole, sometimes we say pole core. But this part, the bottom part, is called as pole face. Pole face. Pole face. Armature, laminated sheet material. Laminated sheet material. Here are the laminations. Laminated sheet, silicon sheet for DC armature. Okay, that's it. You see, there are lots of laminated sheets packed together to construct armature. That is the main magnetic part of rotor. This material is silicon steel sheet material. Sometimes we say laminations because each silicon steel sheet material is isolated from each other by a tiny isolation layer. I mean varnish. Burada yüzeyler arasında incecik bir vernik var. Dolayısıyla bu levhalar, sheetler birbirlerinden varnish ile izole edilmiş. Bu varnishler şöylemesine eddy current'ların akmasını engelliyor. İletimi bozarak. Her zaman tabii varnish kullanılmıyor. Bazen yüzeyde işlem yaparak yüzeyin iletkenliğinde bozdukları oluyor. Ama varnish ucuz bir yöntem olduğu için hala çok yaygın. Yani yüzeylerin iletkenliğini bozan bazı teknikler de var. Here's another rotor. Here's another one. Let me make it more clear. You see sheet material, sheets. Okay. Let's turn back to our topic and try to complete the first session today. Here you see armature. Armature conductors, windings, you see, commutator mechanism. There is a mica insulation material, mica, between the commutator segments. Here are 1, 2, 3, 4, 5, blah, blah, let's say 12 segments of commutator. Here you see a guy under manufacturing. Here are slots. Slots are first isolated by some insulation material, looks white here, and then there are some coils inserted into slots, and coil ends connected somewhere here, I mean commutator, connected to commutator. That is the shaft you see. Okay. You see commutator. You see windings, but the windings here have some white insulation material, so you cannot see copper color. It is not required. Here are some copper conductors, enamel covered, let me proof it. Here you see enamel, MIA, enamel covering on the copper wires. It looks like copper, but in fact there is enamel covering. We should. Here is a tiny armature. You see the sheets, lamination pack. I mean silicone steel sheet. Here you see enamel covered copper coils, copper wires. You see a commutator, and here are commutator segments, and between commutator segments, in fact, here are some mica insulators, mica insulators, and here you see slots, one slot, second slot, another slot somewhere here. I don't know how many slots there, but you see shaft and non-driving end. Here's the output shaft or driving end. Driving end of shaft. Yani mekanik dünyayı buradan sürüyorsun. Drive yapan kısmı burası. Burası non-drive. Sürmeyen kısmı. Armature malzemelerini tanıyoruz. Now here you see lots of armature materials. All those are made of silicone steel sheet packs. I mean laminations. You see shaft, slotted construction. So some coils, here you see, will be distributed from here to here, and then from here to another. I mean, let's say A to A prime, and then B to B prime, and C to C prime, blah blah. But later we will see that it is a bit different from the other machines. DC machines are generally contain double layer coils. Here are two coil sides. So let's say Z prime and Y prime, blah blah. Some parts will be below. I mean from here to here. From here to here. Upper to lower. Upper to lower. Upper to lower. And then some of other ends of the some of other coils will come here, down to here, down to here, down to here. So there are two layers, double layered winding. DC armature coils are double layered winding. Here you see some armature teeth and slots. You see teeth. Those are teeth. Here are slots. Slot carry copper conductors. You see armature conductors, windings. Here are slot liners, a kind of insulation material. Here are fiber edges, fiber wedges, wedge kama demiştik az önce. Fiber wedges to keep conductors inside the slot. We use wedges. Here are wedges installed to keep conductors inside the slots under heavy centrifugal forces, because you know centrifugal forces M and V squared over R, that is the radius, that is the centrifugal force. Those conductors are forced by centrifugal forces. They want to be out of the slot, so we use wedges to keep all those conductors in the slot. Here are cooling ducts. Bir anlamı yok bunların ama burada soğutma, türbülans yaparak soğutmayı sağlıyor. Ona cooling ducts deniyor. It makes some air circulation for cooling purposes. Here's shaft and here's shaft locking wedge. Burada bir başka wedge oluyor. Shaft locking wedge. Şöyle geliyor. Shaft locking wedge. Cooling fan gördük. Non-driving end'de. Burada driving end var. Sürücü uç. Armatürü görüyorsun. Frame'i görüyorsun. Terminal box'ı gördün. Terminal box. Here you see double layered windings. Double layered windings. Do you have any course today? I should stop. I know. In a few minutes. Okay. I will stop in a few minutes. Here are slots. Inside the slot, there must be a tiny insulation called as slot liners. Here, slot liners, yellow ones. Here are slot liners, insulation material. And then here are the armature coils, armature coils. And these coils will have double layer. One part is at the bottom, in the bottom, and the other part will be somewhere in the upper part, up to down. For example, from here to somewhere here, up to down, up to down, up to down. Coils are like this. So there are always double coil sides, double layers. You see commutator segments. Commutator segments are connected to ends of the coils. For example, coil of any, let me find somewhere here. Yes, it is somewhere here. Look at, take care. The conductor coming from somewhere here will be connected to commutator segment. Here is another connected one. In fact, in the complete view, there are always two connections for each segment. There are V shape. All segments will be connected to two conductors, top sides and bottom sides. Here you see top sides of the double layer, and here you see bottom sides of the two-layer winding. Okay, ladies and gentlemen, let's stop here. We stopped here. We will continue later. I want to recommend you some videos. Here's DC machine playlist. I recommend you to watch on manufacturing process, Baldor. There's a copyright issue, so I couldn't play them here because of copyright issues. The manufacturing process can be watched here. And then here you see some other how does it work video. Those two especially are good. And here's an American Army video, 34 minutes, but it is very old, from 1961. Defense Department. DC motors and generators. That is a wonderful video, but there are some a little bit mistakes or different expressions. For example, in those years, in 1950s, 60s, generally instead of current direction, electron direction is used. So there are some confusing parts, but it is a very good video. I recommend you to watch. English is very good.
This position.
I recommend you to watch. And also the Turkish video, I have my lectures. Doğru akım makinenin yapısı, çalışma prensibi. Those are the topics I lectured today, especially the first one, machine parts, introduction will be in this video. So, doğru akım makineleri, giriş ve yapı. I recommend you to watch this video if you have time. Okay, I will continue from here. In case you are having question, please send me. I stop lecturing here.